Assalamualaikum warahmatullahi wabarakatuh. Nama saya Muhammad Syakir Rahman bin Muhammad Khairul Anwar. Nombor kad matrix 076579 daripada Group 5. Saya ingin membentangkan tentang problem explanation pada kes nombor 1, iaitu Campus Road Navigation System. Okey. Daripada gambar rajah yang tertera di bawah ni, kita mempunyai 9 building campus grid lah, di mana startnya dari library ke goal state, iaitu main hall. So objektifnya adalah untuk mencari successfully pathfind across 9 bangunan ini, yang mana yang paling dekat untuk pergi ke main hall. Okay. Misi dia adalah search student must start at library initial state and find route to main hall goal state, iaitu initial state di mana library yang atas kiri tu, dan goal state nya adalah main hall bawah kanan tu. Okay, so movement rules dia adalah student perlu bergerak atas, kanan, bawah dan kiri dia kepada connecting nodes. Contohnya library admin dikira 1 node, library ke hostel dikira 1 node ke bawah. Okay, so itu adalah movement rules untuk case A ni. Okay, so lastly the challenge dia several roads are blocked, means di mana ada certain nodes road nodes ni di block. Ia menandakan X pada jalan tu, so means student tak boleh lalu lah dekat nodes tu kepada nodes lain, sebab dia tidak dapat lalu. So itu sahaja daripada saya. Sekian, terima kasih.
Hello, my name is Muhammad Daniel bin Wahimi, matrix number 077474, and for my part I will explain about algorithm implementation strategy. So let's start with our environment initialization. For this campus navigation system problem, we use Java, and the campus is modeled as an object-oriented agency list. In the problems in Java, we remove the block roads so that it will act as a natural constraint. So for uninformed search, we use BFS with a queue and DFS with a stack, and they blindly traverse the grid level by level or brush by brush without knowing the goal's coordinates. So for informed, we have to first explain about the Manhattan heuristic. Because diagonal movements is prohibited, this calculates the absolute horizontal and vertical grid distance to act as a mathematically consistent compass. So for informed search optimization, we use greedy best first and A-star algorithm to evaluate this heuristic to actively prioritize nodes closest to the main hall, and it guarantees an optimal route while saving memory. Hello, for this session, I will explain about our Java coding. First is the import Java, which is used to, because we need several data structures such as queue, stack, as well as priority queue and hashmap and a few others. The entire program lives inside just one class. Okay, so here we can see the node inner class. This presents a single building on our campus map. Each building has a name like library or main hall. X and Y are just simply grid coordinates. They are simple positions used to calculate the heuristic letter. Next, the path node. Path node is a wrapper to track where we are, how much it costs to get here, as well as the full route taken. The name is the building name. Cost is the number of steps from the start, as well as path is our list of every building visited along this route. Okay, next, the global data structure. Nodes is our lookup table. We give it a building name. Get back is node object with coordinates. Then we have graph. Graph is our adjacency list. Each building name maps to a list of its directly connected neighbors. Okay, next stage is our main method. First, we build the entire campus map using the setup map method, which I will explain later. Then we put our start as well as our goal. Then we print out a few introduction layer, as well as then we run 4 programs together on the same graph and print their results. First, the setup method. As we can see here, there are 9 buildings as explained in the state representation. Then, as we can see here, we only add valid roads. The block roads, we simply remove them because it reduces the complexity, and the algorithm can only travel the roads we define here. Next, the add node helper, add node and add road helpers. Add node is to store building with its coordinates, as well as create anti-neighbor list in the graph. Okay, next, the BFS. This BFS we use queue, which is FIFO, first in first out. This means that we always process the oldest path first, which guarantees we explore level by level. Visited here is a hash map to prevent us from revisiting buildings and getting stuck in the loop. The queue seed here is to seed the queue with our starting point, which is the library. Afterwards, we visited, which we set the library as visited, so we don't add it into the loop. From here, we can see that the main loop. Then we continue with DFS. For DFS, we use stack. Stack is LIFO, which is last in and first out. This is quite similar to how DFS works, which it makes it deep dive into the path before backtracking. So as we can see, we can use push instead of add. Then this loop here again. This loop here is to I believe to visit check after poll and loop through neighbors, copy paste and then add to queue. Then we have greedy best first search. Greedy best first search is sorted by heuristic only, which we use priority queue. It always pick the nodes that looks closest to the graph using only estimate best. As we can see here, the comparator here calls the heuristic node name and goal, which is the method to calculate the Manhattan distance. The loop here is also quite similar to DFS. Next, A*. As we can see here, A* uses the cost and heuristic, which is Fn, Gn, and Hn formula. Then the similar loop here. Afterwards, this is our heuristic, which we look up the grid's position of both the current building and the goal, and we use the formula, which is S1 minus S2 plus Y1 minus Y2. And afterward, we have the print result helper, which helps in printing the result. So we can run the program here. Sorry. Now here we can see the result. All travels to similar path because we have only 9 nodes, and all cost is 4 because we only go 4 paths from library. Okay, thank you.
Okay, Bismillahirrahmanirrahim. My name is Muhammad Ajat bin Azizi, Nomometric 017-526. Today I'm going to talk about heuristic design. Firstly, heuristic function design. We use Manhattan distance as our algorithm to calculate the absolute horizontal and vertical distance from the current building to the target. The Manhattan distance use the formula Hn, the modulus symbol Sn minus S goal, plus the Yn minus Y goal. For an example, we use the starting point, which is the library, which are the coordinate of 0, 0. The target, the goal, is the main hall, has the coordinate of 2, 2. We plug in the value to the formula. We got estimation of 4 steps. Okay, next is the suitability of the heuristic. Firstly, it's because it's the movement constraint. The agent is strictly limited to the moving up, down, left or right. Diagonal movement is explicitly prohibited, making Euclidean distance highly inaccurate. Next, the grid axis alignment. The Manhattan distance calculates the progress strictly along the grid axis. Next is the one-to-one step mapping. because the path cost for every valid move between adjacent building is exactly 1. Thus, this formula flawlessly translates it into a true one-to-one step estimation. Okay, next I'm going to talk about heuristic evaluation. Firstly, the admissibility. A heuristic is admissible if it never overestimates the true cost to reach the goal, which is Hn must be equal or less or the same as H times the N. Our estimate assumes a perfect grid with no blocked roads. Because the agent must detour around the X barrier, the actual required step will always be equal or greater than our estimate. Next is consistency. A heuristic is consistent if its estimate satisfies the triangle inequality condition, which is Hn must be equal or less than C and P plus HP. Since the step cost between the adjacent nodes is strictly 1, the difference in the heuristic between connected buildings is always 1. Thus, it's mathematically proven to be monotonic. Next is the impact on the algorithm performance. First is the greedy best first search. By sorting using priority queue exclusively with the Manhattan formula, the algorithm actively ignores the paths leading away from the goal coordinates. This reduces the node's expansion and improves its time complexity. The next one is the A-star search algorithm, which balances the actual cost with the estimated using the formula Fn Gn plus Hn. Because our heuristic is admissible and is also consistent, A-star avoid is overloading memory with user's path, also called as space complexity, and minimize the iteration, which is the time complexity, while mathematically guaranteeing the shortest path. Thank you.
Next, I will talk about result comparison. So, this is table of 4-element algorithm. So, let's talk about the algorithm we have here. So first, we have 4 algorithm, which is we have breadth first search BFS, depth first search DFS, greedy best first search, and A-star search algorithm. So we have the column not expanded, path opportunity, resulting path cost. So let's talk about the first algorithm, which is breadth first search BFS. So the not expanded for BFS is 9. For path optimality is optimal granted because step cost is 1. So the resulting path cost is 4. Next, the DFS. For DFS, the not expanded is 9. For path optimality is not granted for optimal path by chance, and the result is 4. Next, greedy best first. For greedy best first is for not expanded is 8, and for path optimality not granted but can be trapped by obstacles, and resulting is 4. And the last algorithm, A-star search algorithm. For not expanded is 8. Path optimality is optimal granted mathematically, and resulting path point is 4 too. So that's it for me. Thank you.